So today, let's continue looking into the AGC control. First, we use this example with a two generator connected through a single tie line to discuss how to choose the B values. Earlier, we developed those two formulas based on the governor control only without any AGC. So if there's no AGC, which means the outer loop of this block diagram will not be there. So which means, so we don't have those outer loop. We only have just inner loop. So if there's any change on the load, the delta PL1, for instance, so that will cause the tie line flow change, which is delta P12, and also frequency change, delta omega. So those two values depend on the beta 1 and the beta 2. Do you remember how is beta 1 calculated? What is beta 1? Yeah, basically just, a 1 over R plus D, right? Beta 1 will be 1 over D1 plus, 1 over R1 plus D1. Beta 2 will be 1 over R2 plus D2. So because governor is a droop control, it doesn't eliminate completely the frequency deviation. So you will see tie line flow change and also the frequency change. But now we add the outer loop by adding two integral controller, right? With integral gain KI1 and KI2. We have to give a signal to that controller. So here we call it ACE. ACE stands for area control arrow. We give each controller some control signal. That control signal based on this block diagram, you can know. So we collect frequency deviation and multiply by a factor which is B1, and we also add a tie line flow. Yeah, this is a tie line flow change here. And we use the frequency deviation multiplied by B, another coefficient, we call it B, or B1, B2. Then we add another item, which is either positive or negative tie line flow change. And we create the ACE1, ACE2. And we feed the signal to the integral controller. And the integral controller is going to update the setting point. This is different from the droop control. For droop control, we have constant setting point, but here we directly change the setting point, and eventually we want to eliminate frequency deviation and the change on the tie line flow. So now the first question is, what beta value should we use? The very simple idea will be we go ahead, just take a beta value. We let B1 to be beta 1, B2 to be beta 2, okay, for both generators. Then we just, because now the area control arrow will be simply just delta P12 plus beta 1 delta omega for the first area. And if you plug in those two formula here, and you get negative delta PI1. So this is for the area 1, so which means the first generator need to decrease the generation by this amount. Why? Because the first area has, this is negative feedback control. This is negative, which means you need to increase the generation by this amount. Why? Because the area 1 has a load change. So you have to cancel the load change. So if you calculate ACE2, that's 0, which means the second area doesn't need to do anything. So this is pretty fair strategy. So whoever experience the load change increase or decrease, your generation is going to pick up that load or decrease that amount of load. But the other areas, they don't need to do anything. So we get the conclusion, if both generators have a beta I equals BI, if it simply just take beta factors at the B factors, and the load change is resolved within the local area. Okay, you don't need any help from any neighbors. So now we can generalize the B value. We just simply let B to be let be k times beta. So here we just assume both units will take the same factor, same k. So if we still plug in the delta P12 and the delta omega, we'll get a more complex formula. So this one definitely is not negative delta PL1, but it will be the load change multiplied by a factor. The factor determined based on the k and betas. Similarly, ACE2 will have another factor. So both depend on the change on the load. Okay, so we can put a table by giving a k different values. We can just get some conclusion on the ACE1, ACE2. So if k take 1, so the first factor will be 1, and second factor will be 0. Okay, so this is what we know about using the B values the same as the beta value. But if k take 2, double, so the first one will be 1.5. The second is not 0, it's 0.5. Even it's lower, but which means this here you still need this one will be 0.5. Oh, what happened? All right, this here will be 0.5. So both generators participate in the control. So if you have a lower value, like lower than 1, it seems the first unit only takes 75% of the effort, as the case of k is equal to 1. And second unit take a negative effort. It doesn't do any much positive help. It just try to not to help, and also add some additional burden to the first unit. So if we do the simulation using the Simulink, so when k equals 1, and both unit will the first unit will mainly take care of the load change. The second unit, you see, if you see the dynamic, it basically just stay around the original. Definitely temporarily, it can have a frequency dip, but never go over the nominal frequency. And for the mechanical power, so the first generator will increase the mechanical power, and second generator will roughly stay the same. It doesn't change. And finally, talent flow doesn't change. When you have a k equal to 2, both units actively participate in the control. Definitely, the unit 1 will do much more control. It will be more aggressive. It will more aggressively mitigate the frequency deviation. When k only 0.5, what's interesting is the second unit will simply doesn't want to do any active control, and you see this curve will basically just stay under the nominal frequency. It even increase the deviation of the frequency, but eventually, after taking a longer time, the system still go back to roughly the original frequency. Even it may not be, because this is AGC, so eventually we'll go back to 60 Hertz. So we can have the conclusion. So if B is bigger than beta, so the generator will participate more in regulating frequency. If it's less than beta, it will participate less in regulating frequency. But no matter what value you take, as long as finally the system can stably reach the new equilibrium point, new static condition, frequency will be 60 Hertz. It may have different time performance. Some will recover faster, some will recover more slowly. But recovering faster doesn't mean it will be good, because you will see more oscillation, right? So you need to pick a proper value for B. Okay, next we need to go into the discussion under what situations the AGC is available. It can be a very silly question. So if you send the control signal to the setting point of the generator and through the indigo controller, eventually it will keep feeding that signal until the frequency really going back to the original frequency, right? But that is based on ideal assumption. So there's no limitation about the controller or the capacity of control. But here we have to think about the reality. So we have to first introduce the influences from operating reserves. Operating reserve means if some units they have operating reserve, which means their AGC will be active. Otherwise, their AGC may not be functioning. Remembering we introduced this concept, the NERC balancing authority. Balancing authority is the area defined by NERC. Within each area, you have to maintain the generation and the load balance. And the NERC also require each balancing authority maintain adequate operating reserves. So operating reserve include two types. The first type is called a spinning reserve. Spinning reserve basically just means unloaded generating capacity. So if right now the setting point is PREF, that we call it PREF, which means whatever value you ask the generator to output for the PM, for the mechanical power. And if you increase this value, so there's an upper limit. So that upper limit will be a maximal PREF. So the gap will be the spinning reserve. So for instance, if the right now generator is generating 100 megawatt, but you can increase up to 150 megawatt without causing any violation or reliability issues. So that 150 will be PREF maximum, and 50 megawatt will be spinning reserve. In some other cases, if you allow some load to be interruptible, which means you can have a very responsive load. For instance, there's some customer, they really don't have to use electricity right now. So if you really need a system to reduce the stress, the burden, and you can easily just interrupt those load, like demand response, responsive load, smart meter, or any other load which can become dispatchable. And those load can also consider as a type of spinning reserve. But here we focus on the real spinning reserve, which means the real spinning generation, which is there ready to generate additional power. Non-spinning reserve means it can be reserved, but it can take some time. For instance, if it's a gas turbine, it can easily just start up in 15 minutes. So that reserve will be ready in 15 minutes. But 15 minutes is it's a very brief, but it's too long for governor. Governor need real-time control. Even AGC prefer real-time control. So non-spinning reserve cannot help on governor or AGC, but they may help later for like under-frequency load shedding. So if you want to do emergency control, the 15 minutes is maybe okay, or they can just just pick up those units ahead of time when the system enters some abnormal condition. But we cannot rely on those non-spinning reserve. But here we focus on the spinning reserve. So we may have either sufficient or insufficient spinning reserve. So for instance, in normal conditions, usually we assume spinning reserves are sufficient. Each area need to have enough reserves in order to make sure the AGC is functioning, such as you can eliminate the area control error, ACE. But if one or more area do not have a sufficient spinning reserve, so ACE cannot go back to zero. So they will be there. So which means whatever the ACE will define, that by linear combining the frequency deviation and timeline flow change, so that part cannot go back to zero. So there will be some change in frequency or timeline flow. So then to consider the spinning reserve in our calculation to determine the new timeline flow and the frequency deviation, we have to consider two different scenarios. The first one is when the load is decreased. So if the load is decreased, which means the generation is bigger than load. So if a generation already have spinning reserve and now the load decreases, So which means you will have more spending reserve, right? So spending reserve is not concern at all. As long as the load decrease not too much, you need to shut down some unit, and generator can always maintain the AGC function and governor controls. But for the other situation, if there's a sudden load increase or generation loss, that will make the total generation be less than load. Then whether or not you can maintain zero ACE really depend on how much spending reserve is left. Okay, for instance, if there's a purely just load increase, all spending reserve is there. If you increase load by 100 megawatts, but your spending reserve has 200 megawatts, definitely you can take care of that load increase. So ACE will be zero. But if you have a generation loss, and that generation is carrying some spending reserve, so you're also going to lose that part of spending reserve. So we have to make sure the remaining spending reserve is able to mitigate the power balance. So that will become a more tricky question. So this is what we're going to solve, but later by one example from Kunder's book. From April tutorial, there's a section 4.42. There's a very important sentence. A governor cannot increase generation in the unit unless the unit is carrying spending reserve. An AGC system cannot increase a unit's megawatt output unless that unit is carrying spending reserve. Okay, keep that sentence in mind. So because we have introduced multiple methods to control the frequency, we have introduced the governor. Governor can have the droop control, which is 1 over R, as again to reduce the frequency deviation. We also have frequency dependent load using the D factor, which can also mitigate some load change. And we have a AGC. By using the indigo controller, we can directly adjust the setting point. So there are many ways to affect the frequencies, but be careful. Some ways may depend on spending reserve, like a governor and AGC. All right. Okay, now let's start with this example. I only just highlight some important formulas and sentences from the book, but you still need to read the book. I didn't put everything onto my slides. This is that example. It's a very good example. It integrates almost everything we have learned about how to regulate frequency. So now let's consider two areas. Area 1 has a load 20,000 megawatt and generation 19,000 megawatt. Area 2 has 40,000 megawatt and 41,000 megawatt generation. So if you read the problem, they also tell you for all the load, and we just simply assume D to take the value 1.0. 1.0 here means for one per unit frequency change, it should be 1% of frequency change will cause 1% load change. That's what D equals 1 mean. But you can always translate what I just said into the unit, like how much megawatt change will, how much frequency change in hertz will cause how much megawatt change. Yeah, to be more convenient for calculation. Similarly, R take 5%. 5% also is based on like somehow per unit value. You can always translate the R into like for example megawatt per hertz or megawatt per 0.1 hertz. They also gave you the for the area 1, the B factor assume we take 250 megawatt for 0.1 hertz, and B2 will be 500 megawatt for every 0.1 hertz. Regarding spending reserve, they tell you, if you read through this question, they tell you for area 1, it has 1,000 megawatt spending reserve, evenly distributed among 4,000 megawatt capacity. Okay, 4,000 megawatt capacity of the generators that are running there. In area 2, it also has 1,000 megawatt spending reserve, evenly distributed among 10,000 megawatt capacity of generation. So with those information, available, we want to answer a number of questions. The first one is if we lose 1,000 megawatt load in area 1, assume there's no AGC. So the first one will be simply just based on the frequency droop control of the generator to mitigate this load change. The frequency will not go back to original value, will not be 60 Hertz. Starting from a second problem, there's we'll consider there's a AGC by using the B1 and B2. So for instance, we'll study the loss of same load in the area 1, but with AGC available. And starting from the second sub-question, we consider loss of generation, but that can carry part of spending reserve, which means the spending reserve may or may not be lost due to this contingency. Okay, and later there can be like more loss of generation not carrying spending reserve. So that one can encounter some situations whether the spending reserve is enough to mitigate this loss of generation. If it's not, the frequency may not go back to 60 Hertz. And the next tool will be just tripping the tie line, either using a regional ACE or we can update ACE. Keep in mind, ACE can be updated in real time because ACE reflects how much you want each area to operate and how much tie line flow you want to maintain. If there's any contingency, which means the original ACE settings may be wrong, you can always update the setting. For instance, if my ACE want to maintain the frequency deviation of this area, also tie line flow to my neighbor, but I don't know there's a contingency on the tie line. But if that tie line already out, if already disconnected, why do I want to maintain tie line flow? I can simply just cross off the item in my ACE. I only maintain my frequency, or maybe the new tie line flow from another neighbor. So you can always do that. So last two questions, just check whether you keep the same ACE or you update ACE. All right. So on here in this space, I just list all the formulas we need. We already learned. The first one is ACE is defined to be this combination of frequency, deviation, and the tie line flow change. So here I use the delta PI to the other because the other is basically just another area. Here we only have 2 areas, but if I have more than 2 areas, so for the second item, you need to integrate the export from this area to the neighbors. So if you have AGC, and also it has enough reserve, spending reserve, so you will go back to 0. Otherwise, it will be non-zero. So keep this in mind. If there's no AGC, we just need to, so the frequency deviation can be calculated based on this formula. So this formula came from the power balance. Remembering how we prove, we assume there's a load change that can cause frequency dependent load change, and that will be reflected on the generation change using the governor. So that is the same formula, okay? So we just rearrange the formula. So left-hand side will be the total load change. And the right-hand side will be within this parentheses, basically just calculate the equivalent R and also the total D. So here is like a total, somehow like a total beta factor of this entire area multiplied by delta F will try to mitigate the load change. So next one will be so still based on the power balance, and so because in this example it call each generation of generator as PG, but which is basically just mechanical power. Left hand side is total generation change minus total load change. The right hand side will be the load change on the frequency dependent load and also tie line flow. This is based on the power balance. This is the droop control law. And here is a important formula that help you to translate from per unit value into the actual physical value of the droop control. Because this problem will give you each R to be 5%, 0.05 in per unit. in order to translate to the unit, which is megawatt per hertz, you need to multiply by the power base and also the frequency base. The frequency base is 60 hertz. What is the power base? Power base should be the total capacity of the area. So this capacity includes the total generation right now, plus the total spending reserve. So what is that value? For instance, in area 1, the total generation is 19,000 megawatt. Total spending reserve is 1,000 megawatt. So for the area 1, so this value, for example, will be 19,000 plus 1,000, right? Equals 20,000 megawatt for this value. For area 1, this is just for area 1. For area 2, that one will be 41,000 plus 1,000 will be 42,000 megawatt. So that will be the power base. Okay, so now we are ready. Oh yeah, this is another one to translate the per. It shouldn't be called per unit, but anyway, it just means original D take a value 1. It just means every 1% of frequency change will cause 1% of load change. So it needs to be multiplied by the power, the total load of the area, and divided by 60 hertz. So it will give you the value which is more convenient for our calculation. So let's go to the first question. This is very simple. It doesn't need any AGC. Assume the load is lost by 1,000 megawatt. Okay. So we are going to use this formula to calculate the R values or 1 over R value in with the unit of megawatt per hertz, and we also need to also translate the D value into this same unit. Okay, so from this example, so here we just calculate the 1 over R1, 1 over R2 in the new unit. So this value take the total online generation, which is the generation plus spending reserve. Okay, this is for the area 2. Then we add the two together, we will get 1 over equivalent R. So this tell if we connect two areas together, so more than 20,000 megawatt load will cause 1 hertz frequency deviation. Because 1 hertz frequency deviation is a very huge value. Usually we consider 0.1 hertz, or roughly speaking, it will be about 2,000 megawatt power change will cause 0.1 hertz frequency deviation. Similarly, for the load, we also translate the original value into the new unit, and this number is the total load in area 1, and this is total load of area 2. Okay, so those two can be added together, which give you this one. So purely based on the frequency dependent load, every 0.1 hertz frequency change will cause about 10% of this value. We will be around 98 megawatt. All right, so frequency deviation for the entire system will be the total load change divided by the total beta value. Total beta value is just 1 over R plus the total D. And the frequency deviation is 0.046. So this is question number 1. Any question? The 4,000 megawatt means that's from the problem. That means, so there's a 1,000 megawatt spending reserve. A spending reserve is integrated room for all the generators in AGC. So those generators total capacity will be 4,000. For instance, if there's 2 units, only 2 generators in area 1 connected to AGC, and each generator has some capacity. That's a maximal PREF maximal. You have PREF maximal 1 plus PREF maximal 2. That result is 4,000. And the total room is 1,000. We don't know more detail. We just roughly know this information, but which is enough for our calculation. Yeah. If I have but notice the total generation for the entire area is 19,000, which means only a small percentage of the generation carry spending reserve, or they are actually connected to AGC, not all of units. Starting from question number 2, oh, this is still continue. We still haven't calculated the new Thailand flow yet, but yeah. So this just calculate the load change for the frequency dependent load components. So by using D1, D2, the first area will have load change by 14 megawatt. The second will be about 30 megawatt. Generation, the first area will have change 300 and around 307 megawatt, and the second will be 646. Because this is a loss of load, which means if it's loss of load, the frequency will go up, right? If it's go up, so the area 1, area 2, they're both will have load increase. And the generation need to decrease. Yeah. All right. So finally, am I right? Yes. Okay. So in the area 1, originally we have a 20,000, and after subtract the 1,000 loss, and also there's a positive number which is come from here. That is the load increase due to the increase of frequency. And the new load will, if area 1 will be slightly higher than original value. Sorry, slightly lower than the original value. Because you first lose 1,000 megawatt, but also increase a little bit frequency dependent load due to the increase of frequency. The generation is decreased. And for the area 2, it will be slightly higher than original load because frequency is increased and the generation is decreased. So if you compare this number and that number, the gap is 322.56 megawatt. So this is the new Thailand flow. Originally, Thailand flow is 1,000, but right now the Thailand flow become reduced only around 300. Okay, that is because the area 1 has the decreased the load, and the final frequency is slightly higher than 60 hertz. So this is question 1. So for question 2, we need to add AGC. We keep this formula in mind, so that we can decide whether we can eliminate this ACE value. We still consider loss of 1,000 megawatt load in area 1. Because for the load decrease, it doesn't impact the spinning reserve. Okay, as long as the generation has enough room higher than the lower limit, you can simply just decrease the generation to balance the load. So which means we can easily make ACE for both areas be 0. And the frequency doesn't change. Thailand flow doesn't change. So this is simple. We don't need to do any calculation. It will be for sure we can maintain the 0 ACE and also original frequency. So next question. So now if we lose 500 megawatt generation, that carries part of a spending reserve in area 1. We don't know more detail, but we know originally there's a 4,000 megawatt capacity, evenly carrying 1,000 megawatt spending reserve. But now 500 megawatt of the 4,000 will be lost, which means some spending reserve will be lost. We need to estimate how much remaining spending reserve we have, and then we can decide whether the remaining spending reserve can take care of the loss of the generation. Okay, if it's higher, which means a loss of 500 megawatt generation is not a big deal. You can recover frequency back. So based on analysis, we have 1,000 megawatt spending reserve are uniformly distributed among 4,000 megawatt capacity. So which means for those 4,000 megawatt capacity, we have 3,000 actual generation with 1,000 spending reserve. So this 3,000 megawatt will be part of this generation. Then we can estimate the spending reserve loss. So we have a change on spending reserve divided by the change on the generation. So based on this linear relationship, and so the change on the generation divided by the total generation in area 1, and this will tell you the factor, how much spending reserve is lost, and then multiply by the total spending reserve. We are going to lose this amount of spending reserve. Okay, then the remaining spending reserve will be 1,000 minus that value will be above 800 megawatt. So this is still enough to make up the 500 megawatt loss. Okay, which means ACE can still be 0 for everyone. So there's no change on the frequency of Thailand flow for this case. That's easier. So Thailand flow is still 1,000. The frequency is still 60 hertz for both areas. Question 3. So now we lose 2,000 megawatt generation in area 1, and those generation are not carrying any spending reserve. So this is easier. We don't have to estimate how many spending reserve is left. It's simply just 1,000. But the question will be that 1,000 megawatt spending reserve in area 1 is not enough to make up this 2,000 megawatt generation. But fortunately, we have another 1,000 megawatt spending reserve from area 2. We can definitely use area 2 to pick up the generation. So finally, the area 1 will pick up 1,000, area 2 will pick up 1,000. But how do we calculate the frequency and Thailand flow? So that will be the question. So half of generation loss will be from area 1, the other will be from area 2. But when we see the both area carrying together carry the loss of generation, but area 1, area 2 are different. Area 2 has 1,000 megawatt spending reserve, and they use all of spending reserve to make up the loss in area 1. So during the process of increasing the generation in area 2, it never reached the limit. It only reached the limit at the end, which means during this entire process, area 2 is completely functioning in AGC control. Okay, but area 1 is different. Area 1 has loss of 2,000 megawatt generation, but it only has 1,000 spending reserve. So when it increase the generation to reach a limit, the AGC governor control stop there. So at the end, area 2 has ACE to be eliminated to 0, but area 1 cannot. If you still use this one to check, right? So area 2 has AGC, and it has sufficient spending reserve. Sufficient means a spending reserve is not lower than your desired value. At least it's the same as your desired value. So this is true. So for the area 2, that one will be 0. But for area 1, this is area 2. This is area 1. Area 1 cannot make ACE be 0. So we can do the calculation starting from area 2. So ACE will be 0. So which means this linear combination of the frequency division Thailand flow change will be 0. But it doesn't mean the frequency division will be 0 or Thailand flow will be the same, will be original. How do we calculate Thailand flow? So if this is 0, so we can only have this conclusion, which means we still need to determine the frequency division based on the first area. And then we can calculate Thailand flow. All right. So this is not 0. Because if it's 0, you are not be able to utilize spinning reserve in area 2. Your area 2 is going to send some power to the area 1. So there must be some frequency change. Here is like a decrease of frequency because the generation is somehow lost. And so this is the D. So first we calculate, we're going to utilize the D in the area 1 to estimate the load change due to the frequency. The balance of the generation loss in the area 1 is made up by the reduction in the load and time length from area 2. So here we have this equation. Left-hand side is the total change of the load, and right-hand side frequency dependent. Basically just the delta I multiplied by the beta factor. And also time length flow change. Because for this case, the area 1 will lose the regulation because it doesn't have enough spinning reserve. So this item is not functioning. The governor just stopped there. And if we do the calculation, so it'll be we'll plug in the value here, so we can calculate delta F, which is negative 0.1875 hertz. This is frequency deviation of the entire system. So we bring this value here so we can calculate time length flow. Okay, because the frequency deviation, we'll have a low decrease in area 1 by 62.5 megawatt. And time length flow from here, it will be negative 937.5 megawatt. So this also have the load change due to the frequency in the area 2. So finally, the load in area 1 will be decreased. And area 2 will also be decreased. And generation in the area 1 will decrease by 1,000 megawatt to use up the remaining spinning reserve. And the generation in the area 2 is decreased. It will use up some spinning reserve, but because area 2 still maintain the governor functioning, so it will have some so this will be the new generation. So if you calculate the time length flow, the steady state time length flow from area 2 to area 1 will be 1,937.5 megawatt. The new frequency is slightly lower than 60 hertz. So this will be the new time length flow. Okay. To summarize, for this more tricky situation, area 2 during this process never reach a limit of spinning reserve, even it's almost use up the spinning reserve at the end. So area 2 will maintain the AGC, which means the ACE can be 0. Okay, but area 1 cannot make ACE be 0. So we'll need to determine the frequency based on the entire system, considering the frequency dependent load. For the next case, what if we open this timeline? If we open this timeline and the operator didn't update the ACE setting because he didn't notice the loss of the timeline. So the supplementary control or the AGC of the area 1 will try to maintain the interchange schedule still at 1,000 megawatt, which means it will try to ACE1 will try to maintain be 0. But because we lost this line, the time length flow change, this one cannot be 0, right? That one will be that 1,000 megawatt. So which means that change will also make this, because this one is not 0, this one cannot be 0. So frequency deviation will be -1000 divided by 2500. So that will cause 0.5 hertz, 0.4 hertz decrease. So area 1 will have low decrease. For the area 2, the frequency will increase because they also didn't recover the ACE setting, use the original setting. They try to maintain this net export from area 2. So that will make the frequency increase. So finally, the area 1 will operate at lower frequency, and area 2 will operate at higher frequency. Okay. Although they both maintain ACE at 0, but because Thailand flow cannot be 0, the frequency will not be 0. So one is positive, the other is negative. The last question will be very simple. If we still trip the Thai line, but operator realize the line is not there, so we just update ACE. So which means in the ACE formula, we just simply cross off the item on the Thailand flow. We only maintain the frequency. If this is the case, that will be easier. Okay. So frequency will go back to 60 hertz, which means in this case, the operator just simply remove this item. ACE only is only used to mitigate or to eliminate the frequency deviation. The frequency will be 60 hertz. Okay, any question? That is very quick introduction about this example. I didn't paste all the discussion analysis from the example, so please do read those pages on this example. Okay, so how about we have multiple areas, more than 2 areas. So each area may have more than 1 Thai lines with neighbors. So when you design the ACE, you need to increase the frequency deviation and also include some Thai lines you want to schedule. Okay, so you can, for example, for area 1, you can schedule both Thai line and includes both Thailand flow and also frequency deviation in the ACE, or you can also just include maybe some of Thailand. You can customize ACE based on what you expect for the system. But when you deal with more complex situations with a lot of area, you still can calculate the net export, okay, or net import. So you still need to maintain the power balance for each area to be 0, right? The net export will be equal to the total power leaving this area, subtracting the total power coming into this area. So how to deal with a large system with multiple areas? So we need to talk about the balancing authorities again. So we introduced this concept in the first section. We know in North America there's many large power company, and for large company they can have multiple areas. So within each area, the power need to be balanced in real time. Smaller company may be only based on single balancing authority, but larger company can have many balancing authority. So for instance, we are in the Tennessee state, and so the TVA itself is operated as a single balancing authority. The connection between the balancing authority through tie lines, so there can be some meter. The meter will measure the real-time Thailand flow. When they do the economic dispatch, based on maybe the electricity market, they can determine the scheduled value. And they are going to use the ACE, including the frequency deviation in each area and also Thailand flow change to try to recover the ACE back to 0 if there's any change or disturbance. The control center is the headquarters of each balancing authority, and where the AGC computer system is located. Okay, and all data collected by AGC are processed in the control room through the EMS system. So based on the data, the AGC signals are transmitted from the control center to generators involved in the AGC function. So they can decide the setting point to maintain the generation level. For the AGC system, it's not necessary to regulate all generators. You just need to have a smallest number which is sufficient for this balancing authority to maintain the frequency and time flow. It doesn't have to include every unit. The units that receive a response to AGC signal are called regulating unit. Okay, so a certain percentage of a generator unit are regulating unit, so they are controlled by AGC system. Most of the unit have a governor, so they can respond to the local frequency deviation. And there are also many other units, either they don't have governor, or their governor is not functioning, or their governor is in the deadband. So they don't respond to frequency deviation. Okay, so those are the three type of unit. All right, so this figure gave you the full picture about the frequency response following a disturbance. So here, let's assume the disturbance to be a loss of generator. It's just sudden outage of some generator. So you see, it will start from 60 Hertz. When the disturbance happens, the frequency will decline following this slope. Almost as straight line, linearly declining until certain value. So this value is about negative 30 millihertz, which is the size of the deadband, the governor deadband. So beyond this point, some governor will respond. Okay, so try to do something. So you see this line is a little bit curved, and eventually it will reach some minimal frequency, and they will go back. But if you only rely on the governor, finally it will be stabilized at some frequency near 60 Hertz, but not exactly 60 Hertz. So in the third stage, you need to utilize AGC to bring the frequency back to 60 Hertz. So there's three steps. The first step is just a frequency declining due to the change of generational load and following a slope. So the behavior is almost like straight line. And beyond the deadband, and this line will be curved and to get the minimal frequency and be recovered, but it doesn't go back to 60 Hertz. And then the AGC will try to change the setting point to bring the frequency back. So how do we estimate this slope? So that can be a very important problem, especially for today's power system. You have a lot of renewables, right? When you use renewables to replace conventional generation or take care of the load, and those renewables, they don't have inertias. So they either not having any inertia, or their inertia is actually not directly affecting the grid. Like a solar farm, they don't have inertia. They don't have a rotating part. Wind farm, they have inertia, but inertia can be connected through power electronics. So you don't really see that much of inertia. The power electronic interface to make all the control response become very fast. Very fast response may be good if you in the normal condition, but if there's any disturbance, they can also respond very quickly in the bad way. Okay, so which means they can decrease the slope or increase the slope to make the frequency decline faster. So we go back to this example with a single component. If we model the total generation of system through a total inertia constant H and the total D frequency dependent load here. We already solved the frequency will decline following this relationship. All right. So if there's no frequency dependent load, this is almost like straight line. But if it has a inertia have frequency dependent load, it will finally stop at some largest frequency deviation, but that can be huge, right? It can be much higher than any threshold we can allow the frequency to operate. So this curve, the frequency declining curve, can be solved by this exponential function. So if we want to find out this slope at the starting point when the disturbance happens, so we just go ahead to calculate this first order derivative with respect to time at the time 0. Okay, so we just solve the derivative of this function. So the final answer is this one. So if we use the unit which is hertz per second, that means how much frequency decline in hertz will happen in one second. So that value is delta Pn, which is the change on the power divided by the total double H, right? Double inertial time constant, then multiplied by 60. Okay, so if you're operating the system, and the delta Pm maybe if a single generator outage, it may be 100 megawatt or 50 megawatt, based on the size of generation, and the 2H will be the total inertia of the entire kinetic system. And then using this one, you can estimate this slope. Okay, and typically we assume 30 millihertz dead band. Based on this slope, you can determine how quickly the frequency can decline. So for instance, if right now we have a much smaller H, like right now the 2H is the total inertia of the entire system, but what if we replace 50% of conventional generation by renewable? The inertia will become only half, right? The slope will be double. Slope will be like this one. So it can have much deeper frequency. So that can cause some protection of the frequency. So which means only rely on the governor is not enough. It's not safe to protect frequency. So we have to introduce another way to regulate frequency or control frequency, which is under frequency load shedding. So in many situations, a frequency decline may lead to tripping of steam turbine generators by under frequency protective relays. Remember at the beginning we show there's one chart indicating the integrated time for each unit to operate in the abnormal frequency conditions. So which means each unit, they have some protection depending on the frequency, the real-time frequency, and the duration of the protection can trip the unit, which is good to protect the unit, but definitely bad for the system because that can make situation even worse. So such protections are called under frequency protective relay. They can be also over frequency relays. Under frequency load shedding is just a protection program that automatically trip selected loads. It doesn't directly control the generation, but by reducing the load, it can mitigate the imbalance of power. So if the frequency falls below a specific value, you start just shed some of the customers. So intention of the frequency load shed is not to bring frequency back to 6 Hz. It doesn't allow you to do very accurate tuning of the frequency. Just try to slow down that slope, that frequency declining, right? Such as you can avoid very low frequency So the control is not very, sometimes it's based on the offline design. You can have like 3 steps, so most steps are load shedding based on the slope of the frequency decline and also the real-time frequency. For instance, using the formula we proved earlier slides. So if we know for this system, every second, the frequency will decline by 2 Hertz. Right, 2 Hertz is too bad. Which means if the control is not enough, after 1 second, the frequency will be 58 Hertz. Even you have some governor, the governor will only become response up under some when the frequency is under some dead band. So it only change this slope a little bit, only make the line slightly curved. But after 1 second, you still can have the frequency drop to be very, very bad. So you need to take several steps of load shedding. For instance, one example is when you detect the 59.3 Hertz, which is already higher than the half Hertz protection limit. So you're going to shed 10% of load. If that doesn't work and the frequency continue declining, even the speed is slower, but it get to the 59 Hertz, you need to shed another 10%. If it continue decline to 58.7, so you need to shed another 10%. Okay, any question? All right. So we have 2 additional slides. I just want to give you an idea on how the generations are scheduled of frequency regulated in real time. This doesn't accurately represent the user interface of operators, but I borrowed these slides from a training slides. The training slides is facing the old operator to teach them how to regulate generation, how to adjust the droop control factors, and how to consider the dead band of generator. So you can treat this one almost same as the software interface of operators. So here there's 3 generators. There's 1 generator is dead band can be ignored. So which means the right line, which is straight line. Okay. For the chart, X is generation, the Y is frequency. But another unit, they both have the dead band. Dead band here is around 40, I guess it's around 40 millihertz for each unit. So within the dead band, you see the generation doesn't change. It's just a vertical line. Doesn't depend on frequency at all. But for this unit, it's very sensitive enough, right? No matter how much frequency division, the generation will be changed by the governor. But for the other 2 with dead band, the governor is not changing the generation. But beyond the dead band, it will be a slope. The slope is determined by the droop control factor. So for unit number 1, this is 10%. 10% means somehow like because the slope is -1 over R, right? The 10% will be like -10. And the second unit has droop control factor 7.5%. 7.5% is how much? Yeah, anyway, higher than 10. Huh? Low? No. Let me see. Oh, this figure is different from what we show. Yeah, so basically this slope should be, I think, okay. So this should be, yeah. I think this slope should be 0.1, right? This is 0.075. And this slope is 0.05. Yeah, okay. Because in our early slide, we draw the generation in the Y and the frequency in the X. But anyway, so the third unit is the most sensitive, has smaller R, a bigger slope of control. So Yeah, I also give you the value translated into the megawatt per hertz. The generation setting point is for first unit is 80, second unit is 120, and third unit is 166. And the total load right now is 366. And the frequency is not 60 hertz because there's some dead band. So you can imagine if you if the load is changed a little bit, the first and second unit will not respond to that load change, and the third unit will respond. In order to bring the frequency back to 60 hertz, so there's another step you need to decide to redispatch generation to mitigate that load change. These slides show another example of the existence of the dead band. That's from a paper published by Professor Liu's group. Okay, so this paper did a very interesting study because Professor Liu's group has the newest what is called MMWG model, modeling the EECS connection. So in the model, you have detailed governor sightings parameters. And you can use the model to simulate the event. And also they maintain the F9 devices to collect the measurement data on the frequency disturbance. So they can compare the simulation result to the simulation result, to the measurements. So here, the blue line, the solid blue line is from the measurements. That reflect the true system response of the EECS connection. The second, which is like broken blue line, indicate the simulation result using the MMWG model from the TVA, surrounding the TVA area. So that reflects the most accurate model you have. But if you do the simulation, simulate the same event, you see the blue line is here, and the broken line is there. So they are very different. So finally, the frequency difference will be around this gap. So even the first few swings, they match very well, but steady state frequency are very different. So then they increase the dead band. They try maybe for here 2 different values. The first case, they adjust the dead band for the simulation model to be 39 millihertz. Definitely, they don't know which unit will have dead band, but they can just evenly increase the dead band for most of unit, so to 39. The second increase to 36. So they both have much better match with the real data, right? Yeah. The second case, that's another event. Oh, that's another PMU. Yeah. For that case, the value when they set up the 33 millihertz and 36 millihertz, they gave the best match. They basically create a very narrow envelope, containing the real measurement data. So the conclusion is, for the first event, the dead band will be somehow within 36 to 39 millihertz for the average. For the second scenario, the dead band will be from 33 millihertz to 36 millihertz. Okay, so this is one evidence showing the existence of the dead band of governors. This is my last slide for this session. So next Tuesday, we're going to start the voltage control. Because we already covered a lot of material on like block diagram, designing the control gain for stability. So the voltage control will be much will be shorter than this session. Maybe it may take maybe 1 or 2 lectures to finish. All right.